Ray conditioning, trading photo consistency for photorealism in multi-view image generation, by Eric Chen, Siddhant Holkare, Ryu Yan, Kai Zhang, and Abe Davis. 3D GANs are awesome. These methods learn 3D representations from 2D data and have proven to be effective with a variety of neural representations. One useful application of these models is viewpoint control. To do so, these methods usually first synthesize 3D geometry, then render the geometry from new viewpoints. For example, given these 4 individuals, we can invert them into a geometry-based GAN such as EG3D, then generate novel views. However, this has some disadvantages. For instance, we see that during the GAN inversion process, this model incorrectly reconstructs the geometry of Tim Cook's ear, creating geometry artifacts. His expression is not quite accurate, and details in the skin are over-smooth. These are all common challenges with neural radiance fields, for both reconstruction and generation. One reason why geometry-based GANs may fail is a lack of training data. Because faces are always moving and are often entangled with attributes such as expression, it is difficult to capture multi-view data for faces. So often, the goals of these geometry-based generative models are at odds with the training data. Our insight is that if we only care about generating one image from one perspective, then we don't have to generate 3D geometry, which effectively generates all viewpoints simultaneously. With this in mind, we introduce ray conditioning, a simple method for photorealistic control over generative image models. Compared to the results from EG3D, our viewpoint editing results are more photorealistic. Our method does not need to worry about generating view-consistent geometry, so our results are free of geometry artifacts. So both of these methods control the viewpoint of synthesis, but EG3D does a lot worse here because it's actually trying to solve the much harder problem where every little detail, from his expression to the placement of each strand of hair on his head, needs to be as consistent as possible across all of our views. By letting some of these details vary across views, like you can see with his facial expression in our results, we give the generator much more freedom to create images that are highly realistic. So how do we decouple control over our viewpoint from the use of specific geometry? For each pixel, we represent viewing angle by the direction of a ray through that pixel. And we can encode this per pixel measurement of viewing angle with Flecker coordinates. Our method works by making a small modification to the StyleGAN network. The StyleGAN network first maps a normally distributed vector to a latent space, then uses the latent vector to modulate the features in the 2D synthesis network. Finally, the output image is fed into a discriminator. To condition the 2D GAN on viewpoint, we first compute the Flecker coordinates through each ray through the image's pixels, then concatenate them to the features of the synthesis network. The camera parameters are also passed to the discriminator. To see why this may be useful, let's consider an image editing task. Let's say we have an image of our 2 models, then suddenly a cat appears, and we want our subjects to look in its direction. We can first use GAN inversion on the faces of our models, use ray conditioning to make them look in another direction, then seamlessly blend the faces back into the original photos. Compared to EG3D, our model does not suffer from geometry distortion during the GAN inversion process, creating more photorealistic results. While our method may be less view consistent than EG3D, our method does not make view consistency impossible. When trained on a dataset such as ShapeNet cars, our method can generate smooth viewpoint trajectories of objects. In addition, the quality of our generations outperforms those of light field networks, a prior work which also models scenes with Flecker coordinates of rays. However, we find the benefits of photorealism do not come for free. Photorealism often comes at the expense of photo consistency. For instance, with ray conditioning, when we try to generate smooth videos of faces, we find that viewpoint is often entangled with expression. Aliasing also occurs in the hair and teeth. Ultimately, we believe that our work opens a new design space in 3D image generation, and we hope that our method can inspire new work in geometry-free image synthesis.